Welcome to the pre-recording of lecture 37. So this is our 19th session in this 8-week summer course. Um, in the middle of the 7th week, so we are getting into the last topics in this course. All computers are capable of running multiple processes at the same time. In Python, we can do multi-threading. So this part is rather heavy on computer literacy and terminology. So that's why there are 24 slides. In the first part, I mainly want to introduce some terminology, the difference between concurrency and parallelism, the difference between a process in the thread, what it means for a program to be thread safe, what is a critical section, and what is deadlock. Parallel programming is an entire topic on its own. In this introduction to computer science, it's mainly important that we get the terminology. Okay, what is now a concurrent process? What is parallelism? So, concurrency means that a program is executing multiple tasks independently. So if you are running a graphical user interface, then there is the main event loop. There is the um, program that receives input from the user via the mouse clicks or mouse pointers, and then there are the updates that are happening. Parallelism is that a program is parallel when it can execute two or more tasks in parallel, so at the same time. Um, so one of the examples is parallel Monte Carlo simulation. In Python, there is the multiprocessing module. Now, parallelism implies concurrency, but concurrency does not imply parallel. Here is an example to illustrate the difference between the two. That is the polite dinner conversation. During a polite dinner conversation, people eat and they talk. But since the dinner conversation is polite, there is no eating and talking at the same time. So this is an example of concurrency. Eating and talking are multiple tasks. They are happening independently from each other. They are two threads of execution, if you like, as well, but they do not happen at the same time. So Python can do multiprocessing, but it cannot do parallel multi-threading. We will see why. So parallel processing. So there is the main difference here is that a process can be seen as a separate program. So a program can have several sub-programs in it. Every program has its own memory space, its own data, where its own data is. With threads, so a process can have multiple threads, but all the threads they are running, they have access to the same memory space. Threads are called lightweight processes. So starting a thread can go very much quickly than starting a process. On the other hand, getting threads to run correctly is a lot harder. So there is time sharing. So even on, say, a processor with one core, and I don't think there are many computers like that around, but still, if you are working with a processor, an operating system with one core, then time sharing is a way how you can um, have multiple tasks running independently. It happens then so that the uh, operating system allocates segments of its time. And we have the illusion, since processors are typically extremely fast, that there are so many things happening independently. In the very same way as we look into an animation, we see frame after frame. While this is a discrete process, we have the illusion that everything is continuously evolving. Um, this is more towards the internals of a computer, so we go a little bit back towards the beginning of the course, but this is important to understand what we mean by memory. So the memory contains the code, it contains the static memory, and it contains the dynamically allocated memory that's on the heap. Then there is the scratch space, the stack. So the stack is used if there is a local variable, which is just a number. If fixed, so small, limited size. So the heap is used if you have lists, long lists of data. And a priori, when the program runs, you don't really know before the program runs how long, um, how much memory, how long the list will be, how much memory you will need. So um, the heap is for dynamic allocation. So this slide shows the important difference between the stack and the heap. Stack is last in, first out. Um, a very basic accessing protocol. Um, what does this mean now for multi-threading? Well, the threads, they all share the same heap. They, of course, share the code, but they each have their own registers and they have their own stack. So registers are for um, loop counters, for example, for frequently accessed data. So this is a single threaded process, only one thread of execution. In a multi-threaded process, so this picture here shows that each thread has its own registers and has its own stack. Why is that difference so important? Well, one needs to be careful if multiple threads are running at the same time in parallel. What happens when one thread tries to read something and another thread tries to write something to the same list that is stored on the heap? So what will be important for us Python programmers is that we can share data between threads via references, a reference to a list. So we can't really share numbers. So a number is an elementary data type, and we can take copies of numbers. So that's also to give you an indication while the difference between call by value, call by reference, what we covered earlier, is now so important. It's important to realize when do you want to copy and when do you want to share data via references. Okay, so this slide basically says it in words. So the previous slide was important for the mental image to keep in mind the difference between a multi-threaded process, the stack, and the heap. So parallel programming and working with references is extremely powerful, but one needs to be cautious about this. Um, So both the stack and the heap are necessary. You need the heap for dynamic memory, for memory that for data that occupies a lot more size. With the heap, you could run out of heap space. With the stack is very easy to manipulate, for the computer at least. Um, so the stack is also used a lot in uh, building programs in a data structures course that will become apparent. Synchronization is another issue one needs to be careful about. A stumbling block in realizing true parallelism and therefore also a speed up. So that's actually the motivation why you might want to do parallel computing. You want to get things done faster, but sometimes thread needs to uh, wait on each other. So sometimes it's good if threads have copies of data, so then they can work independently. So that's why there is this stack that is necessary. Okay, here is another important picture. So when we think about the thread of execution, then a thread can be in multiple states. It can be ready for execution, it can be running for execution, or it can be in another mode. This diagram is also important how time sharing actually works, uh, what an operating system does in allocating CPU time to different threads of execution. Many times programs are waiting. They are waiting for the user to do something. In that sense, they are not using the central processing. So then there is another program that can be using CPU time. So the waiting is often when input or output happens. So the program can be waiting for input, but the program can also be waiting for an output device to print something. Um, so to print the prompt, for example. So we have seen in the very early on that just printing hello world with the user being prompted to give a name, there are a lot of actions that are happening. Very little computation. So a process can put itself to sleep. Um, we will see this in the simulations. The process can be blocked from execution. Often it might be the operating system that could be uh, giving the, even if you have a very computationally intensive job, which requires no input nor output, you may get blocked from execution because the central processing unit, that time has to be shared with other tasks that are running on the computer. That is the end state. So a thread can be born. So you make essentially an object in the object-oriented terminology, as we will see. When the thread has finished executing, then it's declared dead. So this is the life cycle of a thread with the various stages. So what should you know from this? What is the difference between waiting and blocked, for example, of a thread? Give a good example. So that could be an exam question. All right, more terminology. So parallel programming is a lot harder. So we say that the code is thread safe if a simultaneous execution by multiple threads is correct. Threads are doing the same computation, the same work as a sequential program, but they do this in a different order. So the order of computations have been very important in ensuring the correctness of a loop, for example. One thing to be very concerned about is that when changing data that is shared, only one thread can do this at the same time. In real life considerations, there are a lot of thread safety concerns. There is the sharing of a bank account. So a banker has to be careful that when two people have access to the same account, if they go at two separate locations to withdraw money, one has to be careful that there is somewhere a lock that is placed. In traffic, there is also a deadlock. I will try to indicate here. If you have an intersection, you have traffic coming in from this direction. You have traffic coming in from the other direction. So the intersection can be blocked when there is here. Um, so you often see this when you write, do not block the intersection. So you may have here a railroad, and traffic is actually, so this is a railroad here. And here there would be another road, but the intersection is blocked because the traffic is blocked in this direction because of there is a train on the tracks here, a slow moving train, and the intersection is blocked. Mailboxes, so we all have different devices. On one device you can read your mailbox, you can delete the mail, then you should also see it deleted on your other device. So there is somewhere a central location where your mail is stored. Database servers, for example, have to be concerned about having different users having access to the same data. So multi-threading is an essential part. So deadlock may occur in traffic. Deadlock may occur also inside a program. So you can have also, this is another occasion of when a thread of execution can be blocked. You can be waiting for memory. So if multiple processes are executing on a computer, also multiple threads, then it could be that threads require extra memory that should be allocated on the heap, but the computer has only that much random access memory, and often if your computer is overloaded, then you can see that everything freezes up. And it's often important that you can monitor this. Here are the conditions for deadlock. So there is the competition for resources that, like memory. So any process, if you have two different processes, they have their own memory. So when one process occupies a part of the random access memory, it cannot be used by any other process. And also with memory can be allocated on a step-by-step basis. And the operating system can, of course, always terminate a process, but it's much harder to actually tell a process to uh, forcibly start to deallocate portions without seeing what the program is actually doing. It also happens in the web servers. Web servers can be flooded by high internet traffic. Here is a classical problem, the dining philosopher's problem. Imagine a round table, and there are 5 philosophers seated, and there are chopsticks next to the plates. So perhaps I can draw this even. So circular table. Here you have 1, 2, 3, 4, and 5. So in another color, there are the chopsticks. So there is one chopstick between the plates. So when one philosopher decides to eat, picks up the left chopstick, picks up the right chopstick and then starts eating. If they are doing this once in a while, that would be working, but here you have a problem with deadlock. If every philosopher at the same time they have realized a breakthrough, or they are just hungry at the same time, so they all pick the chopstick up at the very same time, and there is no right chopstick left. So they're all hungry, so they are waiting for their food. And this is also um, a problem invented for the starving philosophers. So this is another classical programming problem. Happens with parallelism. All right. And now I have defined deadlock and thread safety, but not a critical section. So the solution to this problem is that the requesting of the resources here, if you decide to eat, you should actually have a critical section. So you should enter a stage where nobody else can request a chopstick. So the requesting of the chopstick, once you are requesting one, you enter what they are calling a critical section. And you leave the critical section when you have both chopsticks. The same with withdrawing money from a bank account. Once you have access, the first person who is granted access actually has exclusive access to that account at that point, can only make withdrawals at that moment. All other people are excluded. So the critical section here um, is that once a philosopher decides to pick up a chopstick, the philosopher is granted that privilege, and only that philosopher can at that point pick up chopsticks. That's how you solve this problem. Okay, um, how do we do multi-threading in Python? You can do it without object-oriented programming, but it used to be the thread module, but in subsequent releases it was the underscore thread module. So people wanted, it's most likely not recommended to do this, but it is the simplest way. So this is the hello threads. Hello world is the first program. We've seen the hello world with GUIs. Now we see the hello world with threading. We're going to start a number of threads, and every thread will simply say hello. In this way of working, there is a main thread of execution. We have to be concerned that the main thread of execution does not finish before the threads that are being launched in this process. Oops, here is the critical section. So we do have the critical section that is belonging to this thread module. So you can require a lock, you can acquire the lock, and then in that critical section, these are the instructions that are happening only by one thread. So the system will take sure that here there is the thread safety that is guaranteed here. It's also called a semaphore. Semaphores, I mentioned railway, so railroad signals are also called semaphores. You want to make sure for safety that only one, either the train or the cars, that only one have access to the railroad crossing at the same time. So this is another example in the real world of semaphores and critical sections. In Python, I will not give an example in the code for a lock. I will just mention it. In Python, you have the global interpreter lock. This prevents true parallelism through native threads. Um, so this is necessary because the memory management is not thread safe. So if you want to do true multi-threading, it's still very useful to do. We will see applications of the threading using the thread class. But for true parallel programming in standard Python, so there might be other applications of Python, and also you can, from within Python, you can call compiled code that is multi-threaded. So that would be the solution there. So in parallel execution of code, you have the multi-threading module, the multi-processing module, I'm sorry. Okay, here is how you should actually do it. If you do multi-threading, I will illustrate this in the Jupyter notebook in the second part of this presentation. So there is a threading module, and that exports the thread class. And now it's useful that we have seen object-oriented programming. So this is another illustration of why object-oriented programming, or at least object-oriented thinking, is really very useful, because with this approach you can clearly separate the stages when you make a new thread, when the thread is born, and then when you run the thread. So in the difference with the underscore thread module is that there was no difference between the born and the running state. All right. Designing parallel algorithms is a different course, but I will give one example of a very useful parallel paradigm, that is pipelining. That is the producer-consumer relation. So pipelines, you may have heard about car manufacturing, which is essentially a very sequential process. But if you are doing this in a pipeline, then where every stage in the pipeline does one feature to a car, by having multiple car instances of cars, you can produce cars within minutes. All right, here is another example, producer consuming. So there is the streaming approach. If you are listening to a YouTube video, the YouTube video can be very long, but you are only looking at one specific segment at a time. So while you are consuming, your video might still be downloading. And at the time when you are at that stage, if the video is only halfway downloaded, you can still listen to or look at the first case. So this is an example of parallelism. So you get to watch a lot more pieces of the video, but there is actually not really a true. So there are two processes running. So the streaming and the consumption. So the production and the consumption, and these can be simulated with threads. So this is a good example to illustrate the sharing of data between two processes or two threads of execution that run independently. So there is a pace of the production and there is the pace of the consumption. We will use this as an illustration of sharing data by passing a reference to a list. The list will be treated as a queue. The producer will append to the queue. The consumer will pop from the queue. And it will be another good occasion to see the usefulness of exception handling. So when the queue is empty, the exception will be handled. The consumer will not crash. And it's also a good occasion of sleeping. So the consumer will have to wait a little bit till the producer catches up. Okay, so UML. So What is central here is the class Q. So we have the list, which is the data representation, and then there is the pop and there is the append. So these are the two operations that are already provided. And then we have the use case diagram, where on the queue the producer appends and the consumer pops. It's, by the way, a good exercise. I did this with typesetting LaTeX, but you should probably do this with the UML diagram that is in Jupyter lab. All right. We could simulate a lot more interesting games. So you could, for example, model the simple card dealing games. So where you have games in which the consumer, which is actually the player, can request more cards or up to a certain value. So has the decision to either put the cards on the table or ask one more. So there is the card dealer and then the player. You could also run uh, several algorithms like this. So we have seen the creation of a frequency table. So the frequency table is actually done after the simulation runs. So if you want to check how good the Python random number generator is, typically this still goes fast, but suppose you want to do this for billions and billions of numbers, then you may have to wait with your running and building the histogram, the frequency table afterwards, but you may want to see the evolution of the histogram. Okay, let me now go to the programming part. So I'm 30 minutes in, so the slides were very heavy on computer literacy. So what is important in this course, in this introductory presentation, is that you get somehow a feeling for how to work with threads. So at first I introduce the hello worlds. So here you see an illustration of sleeping. So every thread has a name. So I'm starting a new thread. So there is the main thread of execution in code cell 3 here. This is actually one program. Every thread is created, is made with this function, and it has two arguments. So you see here there is the string. So the names is first thread, second thread, third thread. And then there are the arguments. So the first thread will sleep 3 seconds, the second thread 2 seconds, and the third thread 1 second. Now, this is a simulation. Python is not quite good at real time. It may depend on how slow or how fast or how overloaded your computer is. What is important here is that the main thread of execution has to sleep at least 4 time units, because otherwise the code cell would end, and that would also disrupt, also kill off all the threads of execution. You don't want this. Nevertheless, this is a very simple approach, so that's why I'm still covering it. So this is the first illustration of Hello World with multi-threading. It's not how you should be doing this, so let's just go to the proper way of doing this. So there is the threading module. The threading module exports a class thread, and our hello thread class will inherit from thread. So that means that it inherits the constructor of the class thread. So we have to call that constructor with a name. So there's one argument. So every thread has a unique identification number. Typically, it is really a number. We gave it a name in the previous time, and also here we will give it names, but by default, you would start with 1, 2, 3. There is still the master thread, the main thread that is running, so that's typically thread number 0. Then there is the run method. So run is a method that is a built-in method of the class thread. Unlike the constructor and the string representation, you can also have a string representation that's not defined here. The run actually has no underscore underscore in front of it. So there is just the run. So the run is where you define what the thread is doing. So here the thread will say hello. It will generate a random number between 3 and 6, and then it will sleep that amount of time, typically that number of seconds. So there is the constructor in which you can pass data attributes. So here the main data attribute that we need to pass is a string. That is the string representation of the identification number. But we can also pass, as we will do later on in our producer-consumer example, we will pass the shared queue shared between the producer and the consumer. Okay, let me run this code. So the sleep is in the time module. So the advantage is that with this approach, that I can separate the making of the threads. So I call them 1, 2, 3. Also here you can make an entire list of threads in a list comprehension. You should not be restricted here. And here you see the running of the threads. While this is running, I can indicate the starting and the joining. So with the previous approach, it was a trouble that kind of artificially the main thread had to wait, had to sleep a while. Here we have the join. So the starting is not blocking. So the starting, the control of execution goes immediately to the next thread. The joining is actually blocking. So the main thread of execution will go through, but then you see that the third thread, if you look at the output, the third thread actually slept 4 seconds. But if I would have had more print statements here, perhaps I should probably do this. So thread 1 finished. I just want to indicate that these statements are blocking. Thread 2. Oops. I have to create the threads again because they were dead. Okay, so let's see. Thread 1 finished, thread 2 finished, and then thread 3. So it's kind of in order. But you saw that it took a while. So the threads are started. So the second thread slept 4 seconds. So you see that for the join to, so thread 2 finished actually earlier, but in the join, the statement happened later. So it's only we see the print statement when thread 1 also has finished. So the starting is not blocking. So this runs immediately, but the join is blocking. Okay, so I have 10 minutes left for the simulation of a simple pipeline. So one producer, one consumer. You can have multiple producers, a whole list of threads, and you can also have multiple consumers, also a list of threads. Okay, so here is the class producer. So the producer takes in the name T thread. Q is the list then there is the beginning and the end, and then there is the pace of production. So here there is the first name of the thread, but then there are 4 other data attributes that are going to, so the Q is a data attribute, a proper data, shared data. They're all data attributes, but the A, B, and the P, they're going to say something about the behavior of the thread. So they are going to determine the pace of production. So that's actually the sleeping time. You can have a large variation in the production, or if you, so here I'm just doing rand-ins, so you could also have different distributions. There is a verbosity, so there is the start and the end. So there is the A and the B. So I will produce a number of items. So this is the first class. So let me simulate this. So I have a queue. So the producer starts, it will make numbers 3 to 9, and the pace of production has an upper limit of 10. So the producer can sleep anyway between 1 and 10 seconds. And the numbers that are appended are within the range 3 to 9. So the producer is now appending 8. Okay, so that is a run by the producer thread. So we're doing the bottom-up construction. Each time enforcing the same pattern. We have a constructor inheriting from thread, overriding the calling the constructor of the base class, and then adding new data attributes, also overriding the run. We're going to do this also the same pattern now for the consumer. So the consumer takes in the queue. It will be the same queue. The queue, a list is actually a sequence of names. So we will actually pass the same reference when we make a consumer and a producer. So about the data attributes, the consumer kind of knows in advance how many numbers there are. So it will pop that many times, or will try to pop that many times. And it also has a pace of consumption. So each time it does just the same. So it will, the amount is the number of items. So it will run through this loop. Each time it will decide on its consumption. So it will start by sleeping a little bit, waiting in some sense. Then it will try to pop the first element from the queue. If that is okay, then it will break out this while true. The while true is a loop that reattempts. And here the sleep is important. You do not want, Python actually does not have true parallelism. You do not want that somehow the Python interpreter sees that the consumer is so busy popping that swamps the execution. So you really want to wait a second each time. Okay, so let's test this independently. So I will make a queue of 5 elements, and the time that the consumer waits is also anywhere between 1 and 10 seconds. So I have the first 5 integer numbers starting at 0, and you see the popping. I can't really demonstrate here. The queue is completely static, so we have to rely on our expertise of the exception handling. So the exception that is called here is the index error. Okay, Then comes the final test. So the code is very, very small. So we have a shared queue. We create the producer and the consumer. We start and then we join. So here you see how this runs. And the simulation is rather short. There are only 3 items. And I think at this point I may have, let's see where the exception had. So the wait a second is where the exception happened. So I'm having a slower producer and a faster consumer. So the pace of production is the last integer, which is the 4. So we're making 3 numbers, 1 and 3, 1, 2, 3. Let me run this again. So if I run this again, so this is an independent code block. So we are, so at this point, the exception actually did not happen. So 3 numbers were a little bit. So here, wait a second is when the exception happens. So you see that the consumer here needs 3 trials now for seeing the tree. So in the 3 seconds that it's waiting here, so the producer sleeps 4 seconds. The consumer has already popped 2 from the queue. So the consumer is waiting for the number 3, but the producer is waiting with its production 4 seconds. So that means that also the consumer has to wait at least 3 times. And then the appending happens, the production terminates, and then the consumption will also terminate. So the Python interpreter log is here actually a virtue. So we see all the messages printed one at a time. So when this would be true parallelism, you would see the messages coming up rather garbled. It's certainly if there is no blocking of the output. But here everything went in order. So working with classes, so this is essentially the main program. Working with classes gives a very systematic approach. So we have the 3 stages. So we have the making of a thread. The thread is born here. Then we have the starting of the thread. The thread becomes ready for execution. So it executes. And then we do have the waiting for finishing, so the joining of the threads, after which the threads are dead. We can do this in loops, so we can make whole lists of producers, we can make whole lists of consumers. And I will give an illustration of this in the second half of the session in the next lecture. So what you should remember from this lecture is mainly the terminology. So these 2 diagrams are important. So not that you can draw them. So this is another important picture here, that you kind of realize the importance of sharing references. Also for Python programmers, this is important to know what is on the heap and what is not on the heap.